Hi everyone, my name is Raina Ghazi and I am the Teacher Development Manager for Macmillan Education here in the UK. We have a wonderful guest speaker today called Andrew Jeffrey, who is a Singapore expert who will be delivering our session today. So we will be going through some of the Singapore methods and also talking of Max Maths Primary, which is our Macmillan resource. And then we will leave time at the end for any questions and answers as well. So I'm going to hand it over to Andrew now, and then we will start.
So Singapore maths, let's have a look. People are constantly saying, well, what is it that they do that we don't do? And the answer is probably not much. I think what they really do so well is bring together all the best theories and do it very, very consistently. This was a theme that came up when we ran this webinar a few hours ago. You will have questions, or you may not have questions, but that's fantastic. If you just put them into your chat box, I probably won't stop and answer them during the webinar, but we'll try and manufacture some time afterwards, if that's okay, so that we can answer a few of those. And again, I'll bring Rainer back in on that to curate the questioning. All right, so let's get going. Now, this might sound like a curious thing to ask, but how do you build a house? Well, there's only really one way to do it, and you've got to start at the right place, and the right place is the foundation of that house. Anything else would be obviously a fairly stupid thing to do. Only once you've got the foundations in place can you add the walls, and once you've got the walls on, then and only then does the roof go on, and there's your house complete. Now, effectively, this is what Singapore have done. They've started bottom up and built their curriculum. So they said, what is the foundation of our curriculum? And they went, well, it's got to be the concepts. What do you want in a curriculum? And pretty much they have 6 areas, which, to be honest, won't surprise any of you. Numerical, algebraic, geometrical, statistical, probabilistic, and analytical. Those are the key concepts that represent the mathematical body of knowledge. Once you know what the concepts you want to get across are, then you can start building the skills and the processes that you need. So in our example, obviously calculation, and actually that's first on the list, and a lot of people think that's what mathematics is, but as you can see here, maths is a lot richer than that. It's much more than calculation. If you like, calculations are just the tools by which we can do mathematics. And then the processes, things like reasoning. We're much stronger understanding that communication and language is such an important part of mathematics than we used to be. And then once you've got those things in place, well, then, of course, you can start putting your roof on. And this is not just about what, but how. And in the how, we're talking about the attitudes, both of the teachers and of the students. The Singapore teachers' attitude actually is, we are good, but we can always be better. And that's nice. That's a really good thing to say about yourself. And of course, the other thing is metacognition, which simply means, can I just think about what I'm thinking about? Nothing more than that, really. Students are encouraged to do that all the time. So do we have the confidence? Do we have the skills, perseverance? We're talking a lot about perseverance at the moment, aren't we? And persistence and the value of persistence, the power of yet, something that's happening here in the UK quite a lot at the moment. But yeah, metacognition. You think about what I'm thinking about. How was my learning today? What did I find hard? What did I find easy? What am I wondering? Okay. So first of all, I suppose I should say, okay, now that's their house. And what is their house? Well, it's the house of problem solving, mathematical problem solving. And it's really, really crucial that we understand that that is actually at the heart of the reason we learn mathematics. I think as a species, we've come to be very, very successful on the planet. We've made a few mistakes as well, of course, but basically speaking, we are a successful species because of the degree to which we've become expert problem solvers. And mathematics is really in a unique position to make that possible. So we're teaching children to think primarily and solve problems. Does it work? Does this approach work? Well, you probably have seen lots of graphs and charts and data claiming that it does, so I'm not going to bore you with that stuff. Just a very quick piece of information. In the recent PISA and TIMSS studies that were done, PISA's every 3 years, TIM's every 4, basically looking at progress. So you're 15 if you sit a PISA test, and you're 10 or 14 when you sit TIM's. And as you can see, loads of countries take part, several thousand students from each country. It's a pretty reliable benchmark of whereabouts you are as a measurement of progress. And although here in the UK we don't do badly, I don't know obviously where you are listening to this, but Singapore consistently come out top of those polls. And there has to be a reason for that. Now, I want to throw in, if I can, at this point, a caveat, because you cannot take something from a different culture and plonk it somewhere else and expect it to work. For example, my wife has a beautiful red dress, and it looks lovely on her, but probably wouldn't look quite so good on me. You never know, but I don't think so. And so, actually, the Singapore culture is really important, and this is typically the case in many Asian jurisdictions. But let me try and isolate for you, just in this short time we have, just 5 key things that I think they do well, and more importantly, they do consistently. So let's have a look at those. First of all, they realize that problem solving is not just a bolt on to the curriculum, it is the purpose of the curriculum. And that's really strong. So Barindajit Kaur, who's a very experienced person in the Singapore Ministry of Education, and in fact was a consultant on the Max Math books that Rainer mentioned earlier, she was talking the other day, and I was in the room, and she said there are 3 different things you can teach through problem solving, as problem solving, or for problem solving. Their entire emphasis, and those 3 are subtly different. I'll leave you to ruminate on those, but her entire emphasis is that we need to get our students being able to solve problems. Secondly, the emphasis on visualization. Now, visualization is actually all about just what picture do you have in your mind. When you think about a number, it's very hard to have a consistent image in your head, because you don't know what your image is compared to the person next to you. And as a teacher, you want to know. Those things are called concept images. Do you have a concept image of a number, or does it just look like some digits to you? Thirdly, the emphasis on conceptual understanding alongside factual recall. There's a bit of debate going on at the moment about whether children need to learn their tables and be able to recall them factually and fluently, or whether they should understand what they represent. And to be honest, I'm not sure the argument is particularly crucial. I think actually, I don't think one is more important than the other. They must have them because of cognitive load. If you think about how long it takes you to work out a times table question in the middle of a calculation, that's putting a huge amount of stress on your working memory. So I'm sure you're familiar with the idea of working memory, and it is a very finite resource. It's hard to hold too much. But at the same time, I need to understand what my multiplication tables actually mean, what they look like, why they're the same as division, and so on, and fractions. So we'll talk about that later on. The 4th thing is the spiral development. Now, I'm not sure how clear I was on this morning because we had a question about it, but effectively spiral development of skills and concepts is a very old idea. None of this is particularly new. So spiral means I'm not just going to hit this topic and then forget about it and then come back to it when I've forgotten all about it. Spiral development means I'm going to hit this topic for a while. I'm going to make connections in it because that makes it more memorable. Dual coding is a word for that. And then I'm going to come back to that idea later on, either in this year or next year, but at a slightly deeper level. So we're going to pick it up where we left off and maybe go back a bit. And so I'm constantly revisiting the same ideas, fewer ideas, but more thoroughly. And that's what spiral is. And it's not a spiral on its own. If you know about the DNA sequence, you'll know that it's a double helix. I'm moving my hand around here like I expect you to be able to see it. I can't help that. So excuse me for doing that. And a double helix has connections, or there's 2 different things going on. So it's not just a single isolated thing. And the way they web and map their concepts together is very skillful indeed. And the final thing is this emphasis on CPA. Now, you probably know, but if you don't, it stands for Concrete, Pictorial, Abstract. And this is all about the way that Jerome Bruner, who we'll meet in a minute, introduces us to how children learn. How children learn mathematics when they are young. And it's involving something to visualize, something to do, something to manipulate so that you can get a sense of this terribly abstract idea that is mathematics. And if you're not convinced how abstract it is, I'm going to show you something in a minute which will hopefully help you be convinced. But here's an example from one of the Max Math books. And this is in the book 6, so aimed at 10, 11-year-olds. And you can see that they're using something very physical, something very easy within children's understanding. Jelly beans, there we go. And Samir can make a row of jelly beans, but he can also make 2 rows of them. And you might be able to make 3 rows or 4 rows, depending on how many you have. And then subtly they change it to 7, and she can't make any other rows. So this is a way of introducing the idea that 7 is what we call a prime number, a number that you can only arrange in one particular way, which is so nice, isn't it? I mean, it's so simple, and yet too often we're just taught about prime numbers starting from the definition, and that's the wrong way round, really. So we have Jerome Bruner to thank for this. And here he is. He died recently at the age of 100, so he had a good innings. And he said, look, he didn't call it concrete, pictorial, abstract. He actually called it enactive, iconic, and symbolic, but very, very similar. And effectively, let me show you, if I can, just a picture of how that might look. So here we go. On the left there, you can see some little cubes, and we take 3 and we put another one with them. And then in the middle there, we've drawn a little picture, an image, which shows the 3 and the 1 together. And it doesn't look like a photographic representation of it, but it is an image. And then to the right, what looks like some kind of cherries. Its proper name is the part-whole diagram, which you may be familiar with. And we'll show you in a bit more detail that as we go through. And then on the right, this 3, and then a kind of 2 lines that go across each other, and then a 1, and then 2 lines that run parallel to each other, and then a 4. Now, you and I can read that fluently. We've learned to read fluent mathematics, but it's dangerous to assume that everybody has. And so that is actually an equation, although we don't always say, oh, it can't be an equation, it hasn't got x in, some children will say. So that's how he said it's good to build new concepts. But there is a caveat here. I just want to put that caveat in because I think while people will generally get on board with that educational theory, as the Singaporeans have, actually we've got to be a bit careful. What it doesn't mean is when I am small, when I am quite young, when I am just learning mathematics, when I'm a bit weak, it doesn't mean I have to use all the equipment. But then slowly I kind of get a bit older and maybe a bit cleverer. And once I do that, then I don't have to. I'm going to click and see if I can move my little tray. There we go. He's left that childish thing behind. Isn't that fun? Okay, and it's gone. It's got. No, that's it. I'm too mature for that now, and oh yeah, that's going as well. I'm too mature for that. I've just got to work purely in the abstract symbols. Well, that's not what he ever meant to say. It's not what he meant. I think my understanding of what Jerome Bruner said is this. He said, look, when you come up against a new idea, why don't you start by considering how it would look if you could represent it physically? And then when you've done that very, very quickly indeed, perhaps within the same lesson even, you can also consider how it looks in pictorial format. And then if it doesn't, you can go back. There's no, if you look at this diagram, there's no train, there's no linearity to this. And you can move between those representations. And there I am, of course, happily building my 3 + 1 = 4 in a more abstract way. But if that doesn't work, I can go back in. And this is quite akin to what Jean Piaget would talk about our understanding of the world, I think. So in case this doesn't make sense just yet, I'm going to show you something now which I think acts as a metaphor for just how hard 3 + 1 = 4 is for us to truly comprehend when we are thinking about mathematics. And the metaphor's a strange one. It's all about my hometown. Now, if you've got very good eyesight, you might be able to read it. It says Brighton and Hove on the side of that bus. So that's the city I'm lucky enough to live in, down in Sussex. And you'll notice if you live in a city that public transport is everywhere because the roads are crowded and it's difficult to get around. So it makes sense to use a bus. And consequently, young children who go on buses understand the bus very easily, very quickly. There's not much to misunderstand, is there? It's like a car, except you're slightly freer to run around and shout and get into trouble and enjoy yourself. And basically, young children learn about a bus through the principle that I call kinesthetic investment. Now, the principle of kinesthetic investment is simply, if I do it, if I physically do it, it's like walking up and down a number line. I understand the nature of the inverse direction. Okay, fine. Now, once you've been on a bus, a curious thing happens in your brain. If you see a photograph of a bus from a totally different city, now there's a city you may or may not recognize, there are some clues on the signs there, but if you see a bus from a city, even if you've never been to it, there is enough about it that makes it feel as though it's a bus. You can see the similarities. You can find what is invariant. In other words, what hasn't changed. Maybe the colors changed, but the basic shape hasn't changed. The function hasn't changed. The purpose hasn't changed. The key features, like it's a people carrier, haven't really changed. So you understand, moving from a concrete experience to a pictorial reference, you understand that you're still thinking about a bus. When a child sees a small picture of a bus in a book, it doesn't go, oh, that's a tiny, tiny bus. It's just a bus. They can scale effortlessly. Then, of course, what happens is, if you are lucky enough to live in the United States of America or in Canada or anywhere else they have yellow school buses, then you see, oh yes, okay, I get that. I can see I can see that's a bus. It doesn't look like a real bus. It's clearly just a cartoon. There's something very worrying about the fact that I can't see out the front windscreen, or that the back wheel doesn't appear to be attached. So it's probably just a metaphor for a bus, but it'll do. I understand that that's a bus. And when children watch cartoons, they know it doesn't look real, but they know it's real enough. And so finally, we come to this. Now, here's the problem. Those three symbols together do not look anything like a bus. And this is why it's so hard to learn to read. And the way you learn to read is by looking at pictures. It's funny, isn't it, that we learn to read by giving children books with no words in. And I think we do that, and we point and we say the word, so they get to hear the word, they get to practice the word. And then slowly we start putting the word underneath the picture or next to the picture, so they make those links and associations. And only then do we start to reduce the amount of picture and increase the amount of text until a child can read independently. So you see how hard it is. And in effect, this 3 plus 1 equals 4 idea, which Bruno talked about here, is effectively the BUS of the mathematical universe. That doesn't look like a 3. It doesn't. Does that 3 look 3 times the size of the 1? I think the 4 looks about the same size as the 1, and so on. So it's not at all obvious. Okay, so another really good example then, the very first couple of pages in Singapore, I should let you know that in primary school, almost all, not all, but almost all, 85% I think of schools use a book called My Pals Are Here. And the first couple of pages look very similar to this. This is actually from Max Maths, the Macmillan offering for you guys doing the international curriculum. And very, very importantly, here we go. We've got one robot, and we show that that's represented by one dot, two footballs, two dots. But we've not just got that, we've also got the numerals and the written word. So we see lots and lots of different ways of associating those numbers with their magnitudes. And this is fine, of course, for one-digit numbers. And so although that looks very, very simple, what you'll notice is the clever use of variation. Now, variation is something that's not been talked about for a huge number of years as much as it should have been. I think there's a few people who have been talking about it, but actually, generally speaking, it's only really coming to the fore to the teacher body in the last 20 years. It's actually something that we're probably doing anyway. And one way of talking about that is to introduce, sorry about the text, got a bit wonky there. It just says he's the second of my mathematical heroes. Now, being British, we're not great at pronouncing foreign names, so I'm going to give it a go. His name is Zoltan Dinesh, but most of us just call him Deans. There we go. He's Hungarian. And when we think of Dean's blocks, I'm thinking almost all of us would think of these. Now, these blocks here where we've got ones, we've got tens, and hundreds and thousands and so on. Incidentally, just a little tip for you, those white ones, ones and the green ones, tens and the blue ones, hundreds, and the red one is 1,000. firstly, a little tip. If you have the plastic Dean's blocks and you accidentally knock one of the 6 faces off, as I did, and it's hollow, what you've got there is exactly a litre. Now, that might not change your universe, but it might just make one of your capacity lessons a little more exciting. Next time you fill up your tank with fuel, you'll know exactly how much you're paying for. The other thing that I've had some fun with recently is pretending that the blue one is worth 1, because after all, you can pretend anything you like. They're just made up bits of equipment. And if the blue one represents 1, then you've got a really nice understanding of tenths and hundredths, because the green one is a tenth, the yellow one is a hundredth, and it's fantastic for percentages as well. So just a little aside there. But Zoltan Dinesh was very keen that we didn't just think about the number 10. Now, these are great, and we've used them a lot here in the UK, and I'm sure you may have used them as well. But actually, what he was much more interested in is the structure of the relationship between the different columns. Now, if you're lucky and your school's been around a while, you might find at the back of a cupboard some Dean's blocks that do not work in tens. If you look at this example, for example, excuse me, excuse me, if you look at these, you'll find 1s, and then instead of 10s, 4. So we say this is base 4. And all the base means is, what's the multiplicative relationship between the columns? So if you look at the 1s column, that's just 1s, and the next one is 4, the next one is 4 of those, and the cube there is 4 of those, and so on. So it would actually be 1s, 4s, 16s, and 64s instead of 1s, 10s, hundreds, and thousands. Once you understand that, you get away from this fixation on 10, and you realize that actually it's much more about the relationship between the columns. How might you use that? Well, here's a typical lesson using this CPA approach and Dean's work. You'll see this is a photograph from an actual lesson with some 7 and 8-year-olds. You can see, actually what you can't see is the dice that was used to generate random numbers. And those numbers were created using hundreds, tens, and ones. Notice too the arrow cards, the 300, the 41, the 551, and so on. Something I want to say about the numbers. What's lovely about using Deans with arrow cards is this variation of, I'm talking about the same number, but I can see different things. And I think in this photograph, which is one of my all-time favorite photos, that sounds really sad, of mathematics lessons, I should probably say, is it's very clear, or it's easy to see that each digit you can see in a 3-digit number is actually an adjective. Take the yellow 4, for example, at the top. That means 4 of something. So if you want children to really nail down place value, can I suggest you play this game with them? So show them a number such as 341 and say to them, all right, that 4, what does that say? And the answer is 4. It just literally says 4. And then you say, okay, but what does it mean? And what it means is 4 of something, 4 of, and because it's the second digit from the right, it means 4 of those sticks. And those sticks are tens. So it means 4 of those things that we refer to as tens. So what does it say? 4. What does it mean? 4 tens. What's it worth? 4t, which is a weird word, isn't it, that we use? Okay. Let's look at the 3. So what does it say? 3. What does it mean? 3 hundreds. Don't forget the S. It's 3 of those hundreds. And what's it worth? 300. And I think that in itself is a really, really useful tool. Now, let's have a look at how the book uses Deans. You'll see here's a book 2, grade 2, where count the tens, count the ones. It's very simple. They've used different colors, but they haven't varied much else. They haven't varied the structure. And that's crucial. Vary one thing at a time. What about on the right-hand side? Count the tens, then count the ones. Now here, they've not varied the structure either, but they have used variation because this is what we call perceptual variation. In other words, the idea is the same, but the resource is slightly different. And there are different types of variation. The rule, generally speaking, when you're giving students questions is don't vary too much. Don't mix the concept and the resource all in one go. That's too much, and it doesn't allow children to see what stayed the same and what has changed. I hope that's fairly clear. Now, let me show you an example from Key Stage 2, as we would call it, the higher age group. So here we're looking at sort of 9-year-olds. And now look, we've taken the concept to another column. But actually, if you understand the concept, I'd say further columns to the left aren't actually any more complicated. It's just 5 of those yellow things isn't any more difficult to understand than 6 of those red things. So here we've got 5,609. You can apply those 3 questions. If you like, what does it say? What does it mean? What is it worth? Don't forget the little nuanced thing. The 5 means 5 thousands, but it's worth 5,000. And I think that will help your children understand. Because there's different levels of understanding. I want to talk about different levels of understanding, if I may, for a bit. For example, I could teach a very small child the word diplodocus. And in fact, I have taught several small children, mainly my own, the word diplodocus over time. Not that they have paleontology degrees, but because it's just a fact. And I can name that fact and I can say, this is a thing, this is an object. Yeah, a bit like a bus. So here we go, factual. I know that. I know something. I know that this battle was here. I know that my auntie's called that. I know this. It's a fact. It doesn't require any understanding other than the ability to recall information. Okay, but then we go a bit deeper. Now, procedural knowledge, and this is about, it's important. These first 2 are all about fluency, mathematical fluency. So I have to be able to recall things fluently, but also not just facts, algorithms, procedures. These things are important. They're not mathematics, but they are in effect the tools of mathematics. Can I do multiplication? Do I know how to do addition? Have I got an efficient method, whatever age I am, for division? So this is about fluency. I know something. I know facts. Procedures. I know how. I can carry out a task. And these things are important. But deep knowledge is about the concept. Do I understand the actual idea? And conceptual understanding, now this is good. This allows us to reason, and it's actually, I know why. I know why I put a 0 there when I'm doing long multiplication. I know why moving things along appears to make them 10 times bigger. I know why adding fractions with the same denominator, I only add the top numbers together and not the bottom. Not just how, because that's going to lead to fewer errors. Okay, so there's different types of knowledge, and those are the 3 key areas. And I think what sets the Singapore curriculum apart is they, like many of us, do the first 2, but they're very good at the 3rd one, right from an early age. And I know we all aspire to that, but sometimes we feel we don't have time, and yet they think, no, we will make the time. That's very much a strength of their curriculum. So here's an example. Calculations. We know, generally speaking, at primary age, there are 4 different things that we need children to do. But actually, and that's addition, subtraction, multiplication, and division. But actually, if you think about it, each of those pairs up quite nicely. Look on the left, there's the cherry diagram, the part-whole picture that we mentioned earlier. Now, let's think about this. If I tell you either of the 2 parts, or if I tell you, sorry, both the 2 parts, in this example, I've put 17 and 3. Can you tell me the whole? And of course, you probably can. How can you? Well, because you understand the relationship is that the parts make the whole. So you've got 17 as one part, you've got 3 as another part. So you're really happy that 20 is the whole. And we call that game the game of addition. It's not the most exciting game in town, but it's important. However, if I told you only one of the parts this time, but I also told you the whole, such as in this example, you can still find the missing number because you know the whole, 17, you know one of the parts, 3, so you know 3 plus whatever's behind the question mark makes 17, and then your question becomes, all right, what is it that I have to add the 3 to make 17? And you realize that you find that by doing 17 minus 3, and so subtraction is basically addition with its, looking through the window from the other direction, if you like. And that's a really powerful tool. And I think that's the most important thing about that particular diagram. Now, if that's the part whole, what happens for multiplication and division? Well, you can see it's similar but not identical. And this is what I call the product factor relationship. Again, 6 times 7 being 42. So 6 and 7 are the factor pair that I've used for 42. There are other factor pairs, of course. And 42 is the product meaning the number that you get when you multiply 2 numbers together. And I know so much more. If I know 6 sevens are 42, I know 42 divided by 6 is 7. I know 42 divided by 7 is 6. I know a sixth of 42 is 7. A seventh of 42 is 6. I know that if it costs £6 to make a trip and I make it 7 times, it'll cost me £42, and so on and so on and so on. Okay, so those are the two key relationships. I think that's one of the top most important things I would ever want to say to teachers about calculation, if I'm honest, that picture there. Okay, how does that look? Well, even look, right from book one, they're on it, right from book one. I think this is really important. So 3 red helmets, 3 yellow helmets, 3 and 3 make 6. So the red part is 3, the yellow part is 3, altogether the whole is 6. And again, notice the variation here. It's still 6 on the bottom, and there are different ways to partition 6. This comes as something of a surprise to people, and yet what this is setting up, it's preempting efficiency. I'll tell you why. Supposing I wanted to do 15 plus 6. Now, in my head, I might put 15 and then count on 6. But look what this is training me to do if I'm learning number bonds as well. If I say 15 plus 6, if I say to myself, do you know what? I know 15 plus 5 because that's number bonds. So that would be 20. And I've only got one more, so that will be 21. It just saves me having to do all that counting on. Another example, the one I often quote is 17 plus 5. And when I say 17 plus, I say, you should really be hoping for 3, right? And they go, yep. But it's 5, which is just 2 more. So if I can partition 5 into 3 and 2, it means I've got 17, 20, 22. And it really liberates children from having to count slowly and often inefficiently as well. A little bit later on, I wanted to show you this because I particularly like this exercise. Heads together, so this is like a paired activity. I'm a big fan of paired activities, not all the time, but often, because of what it does to your confidence, and it makes you more willing to be a risk taker if only one other person can see you possibly fall. Not literally fall. But the variation here is very, very good. And I was listening to a talk by Professor Anne Watson earlier this year from Oxford University. And she said variation for me is really about making something available to be noticed. And that really stuck out when I read this page in the Max Math book. So what is available to be noticed here? And if you look, what do you notice 6 times? Now, this is very, very clever because you might not realize, but this is discovery, but it's guided discovery. There is no chance of not making the discovery. And I think children will notice other things, I'm sure they will, and a good, confident teacher whose subject knowledge is good, whose pedagogy is sound, will have no difficulty picking up and running with those. But this is very, very supportive of the teacher and of the pairs. What do you notice? What do you notice? Pick up 2 cards that are even, and they'll find out that the sum is always even and the difference is always even, as opposed to what I was told, which is odd plus odd equals even plus odd equals odd, and so on. So I think that's a very clever use of variation theory there. Okay, so actually, let me just talk to you about this man now. So he is Lev Vygotsky, and he's most well known, probably amongst other things, for his zone of proximal development, which sounds very intimidating, but it's really just scaffolding. And Vygotsky invented scaffolding. He didn't invent scaffolding, the Chinese invented scaffolding, but he invented it as applies to this. And let me try and show you my take on exactly how that looks, because it's a little bit different to some, but over time we can do a lot. Now, before you shoot me and go, hey, the vertical axis isn't right. The vertical axis has got no label on. You're right, because it's got so many possible labels. It's got what I can do, what I understand, processes I can do, procedures I can do. And the only important thing about this graph really is that as time goes on, we can do more. And I know before you tell me, it's not linear. It's not linear. I know that. I know learning is not linear. But generally speaking, the trend is upwards if we are open-minded. So let's put somebody on the line. Here we go. Now, this person is on their journey through time and through life. Let's put something else on the line. Let's say there's a fixed point on that line at which point I'm going to learn my 10 times table. Now, the 10 times table at the moment for that person, assuming they're moving up the graph from left to right, is not easy. It is, I mean, you can see literally on the graph it's beyond them, and metaphorically it's therefore also beyond them, which means it's not easy, which means I have a very, very convenient description of easy, which is everything up to and including what I can do. There we go. But therefore, hard is everything beyond me. And so you can see the 10 times table is hard. But watch this. What I want to show you is this. As I move through life, my easy camp is going to increase. Forget about hard. There'll always be hard. There'll always be difficult stuff for us to learn beyond us. But that's fine. That's what learning is. Now the 10 times table, although it hasn't changed itself, is easy for that person there, not necessarily for that person's sister or brother or auntie or whatever, but it's definitely easy for that person. And that's a real growth mindset thing. Now, Vygotsky said, okay, your zone of proximal development is basically here. Now, I wonder if any of you have ever been to a gym and you've tried to lift up a weight only to find that it's actually very easy. Well, if it's very easy, you can do it, and you can do it lots of times, lots of repetitions with that weight, but it's not doing you any good. Similarly, if it's very, very heavy, not only can you not do it, but you risk harming yourself trying. And so the personal trainer will go, hey, that's too easy, try this one. Oh, that's too heavy, try this one. And actually what they're doing is nailing down your zone of proximal development. That's all it is. Am I in my comfort zone, i.e. too easy? Just I'm happily collecting ticks in my maths book. Am I in my danger zone where everything's a struggle, I can't do anything? Or am I in my challenge zone, my zone of proximal development? And that's something they're very good at in Singapore. And they absolutely focus on whether you understand what you're doing, because if you understand what you're doing and they test for that all the time, then you're much more likely, I think, to be able to challenge yourself on a slightly tougher question. So here's an actual real life example. This is from a lesson I was privileged to be sitting in on one of my trips to Singapore. And I want you to focus on the triangle at the bottom of this whiteboard, please. And the teacher had stuck this out. I like the way she'd prepared them in advance. She'd laminated them. She thought about the questions they were going to do. And that triangle is isosceles. Notice the little red lines she's put on there to show that if those two little bars are on there, that's like a code, meaning these two sides are the same length and therefore the two base angles are the same. So, and now she said, how might we find angle C there on the bottom left? And I was really struck by the boy who came up to answer this question, because as you can see, he wrote 180 minus 30 equals, and then he sort of underlined his answer, even though he hadn't done his answer. Now, this is the antithesis of show your working, where we nag children to show their working. He's showing his working, but not anything else. And then the answer, he's got that from saying the 180 degrees is the full three angles in a triangle, and he's taken off the top to give him the base angles. And then he's realized that if he divides that by 2, he'll get what angle C is because of the symmetry of an isosceles triangle. This is excellent. He's just written the answer, divided by 2 equals. But then what I was really fascinated by, and I think this maybe sums up the whole approach in Singapore brilliantly for me, he didn't even bother to go back and write in the 150, 150, and 75. It was as if like, the rest is trivial. And I thought he's probably going to get told off now, and he didn't get told off at all. He got praised. And then I thought back and I realized how I'd missed the point, because in my head I'd assumed the teacher had said, who can find angle C? But actually thinking back, she didn't say that at all. And if you wind back your recording of this webinar, you'll find that's not what she said. She said, who can tell us how to find angle C? And that is exactly what he did. He told us how to find it. And I thought, well, of course, because if you think about most of the questions you ask your students in maths, you already know the answer. So you're not asking because you want to know the answer. You're asking because you want to know if they know the process. You don't even care what the answer is. I'm not emotionally invested in that triangle, and I'm sure you're not either. So for me, that was a real eye-opener. It's, yes, I've got procedural fluency, but I understand that it's all about problem solving. And if you're interested, they did go on to solve some problems independently and in pairs themselves. So I think that's perhaps a good place to stop and give us plenty of time to answer questions. So I'm going to hand it to Rainer now. And you can kind of start curating these questions. So if there's anything I haven't explained, I'm really sorry. If there's anything I don't know, I'll just say I don't know. Nobody knows everything. Oh, except my teenagers, maybe they do. But there you go. So I hope that's been useful. I hope it's been a kind of just some sort of taster really of how they approach things in Singapore. I'm almost certain you'll have been nodding along and going, yeah, we do that too. Yeah, we do that too, which is absolutely great. I'm sure there's really good practice going on around the world, but sometimes it helps to focus in on just what it is they're doing and why. So, Rainer, I'll hand back to you. Shall I unplug this? Okay.
Appreciate it. Andrew's been with us since this morning. We had a fantastic reception to his webinar in the morning, so we appreciate your time this afternoon in the UK as well. So if you have any questions, please feel free to write them in the little chat box, question box, and then what we will do is I'll be able to show Andrew the questions and then he can have a look as well. Okay, so I think we may have a question here.
Okay. Actually, shall I use the audio?
Yes.
Okay. I might sound slightly different, but it's still me. Right. Oh, glasses on, I think. Right.
There's one question.
Okay. Some students, the weak ones, they get confused when they take, for example, addition in more than one way, like partitioning and using the systematic way. Right. Let me try and work out what the question is.
What to do in this case?
Oh, what to do in this case? Okay, that's quite an interesting question. That's about remedial work. It's not something that they do get confused on in Singapore, simply because of the. And maybe I didn't stress this enough, so apologies, Samar. Actually, they all attack it the same way. This is this thing I said about 85% of schools using these books, but even the ones that don't, they all see addition in first of all little individual items where they put them together, and that's called aggregation, and then they start building from the larger amount to the total. That's called augmentation, and it's very consistent. It's in a horizontal line, then it's with deans, and so on. So they don't really get confused. If your question is, what about children who are learning this new way? Then that's more challenging. I don't know what I would do in any particular case. I'd have to look at that child. When you say the systematic way, I guess you're talking about columns. Is it column addition? I don't know. So I'll come back to you if you can if I haven't really addressed what you wanted, then please do come back to me. Okay, thank you. Oh, there's some very kind comments coming in. I like those. There we go. Oh, we like those. Thank you. Okay, clear. I like that. Here's one from Homera. Would it be right to say the teacher must move backwards from solution to problem before her lesson to understand process? Oh, what a great question. Not necessarily, no. Sometimes it depends on the teacher and the problem. Sorry, that's not a cop out, but it does depend. I think what the teacher must do. Well, you've gone with her, so I'll stick with her. But what you must do, I think, is work the problem yourself. And even if you are very competent mathematician, you need to have gone through the steps yourself. And backwards or forwards, either way's fine, actually. Either way's fine, as long as you've done it. And the crucial skill is anticipating potential pitfalls. That's really important. So, yeah, thank you. Right, are we doing any more questions? No?
If there's any more questions, feel free to write them down. Otherwise, you are more than welcome to send us across an email as well at internationalcurriculum@macmillan.com. So we are nearing the end of the webinar. So I'd just like to take this opportunity to say thank you very much to Andrew. He's been with us all day today and he's been fantastic. And as you can see from the feedback as well, I think it's been very informative.
Oh, can they see these comments as well?
Yeah.
Oh, good. Oh, well, thanks, Teresa and Sharon. Then I'll buy you a drink next time we meet.
So that'd be great. So thank you very much for your time, Andrew, and also thank you very much to the participants as well. We know we appreciate your time as well. And if you would like to claim your CPD certificate, please email the contact details at internationalcurriculum@macmillan.com, and we will be able to help you with that as well. So thank you again.
Yep, thanks for coming.
And hopefully look forward to having many more sessions with you soon. So thank you.